4 millimeters.
Okay.
And then after that, it says find the resistance at 1 gigahertz.
All right. Yeah. Actually, this is a good problem because it's a wire, a standard wire. They give you diameter, and they want the resistance per meter on this thing. So when you talk about DC resistance, and this is always true. If the cross section does not change versus length, it doesn't matter the shape of the cross section. Y'all hear me on that one? Doesn't matter if it's square, round, elliptical. The only thing that matters is the area. So it's always proportional to length, inversely proportional to area, and inversely proportional to sigma. Now sigma for copper is 5.8 times 10 to the 7th, and the units are either Siemens per meter or 1/ohm meters. Now that's resistance for any given length. If it's per meter, it'll just be 1 sigma and then the cross-sectional area. Well, the cross-sectional area, if it's a standard round, or I should say a wire with a circular cross-section, it's just pi a squared if a was the radius, or pi d squared over 4 if it's diameter. Follow? So I'll take the radius as 2 millimeters. So it's going to be pi times 2 times 10 to the minus, see, that's millimeters, so it's minus 3 squared. And sigma here is 5.8 times 10 to the 7th. Can you just tell me what that is? It's going to be small, very small. 1.372 times 10 to the minus 3 ohms per meter. Okay, sounds reasonable. Now, when we take a look at the AC resistance, the first thing we have to do is calculate the skin depth. And skin depth is something you're going to have to know for Friday and for the final. It's 1/square root of pi f mu sigma. Here, sigma is copper, so it's 5.8 times 10 to the 7th. Mu will just be mu naught, which is 4 pi times 10 to the minus 7th. Let's see. The frequency you said is it 2 gigahertz?
1 gigahertz.
All right, so it's 10 to the 9th hertz. And can you give me that skin depth? I want the skin depth first. This is just a standard problem, but it's very good to do this. And be sure you can do this without any hesitation. Make sure you can do this.
2.09 times 10 to the minus 6 meters.
2.09 times 10 to the minus 6 meters. So it's 2 micrometers, or 2 microns, right? Now, you come over, and when you're doing an AC resistance calculation, in order for this thing to work in the approximations, you have to make sure that the radius itself is much, much greater than the skin depth. And in this case, it's obviously true, because the radius would be 2 millimeters, right? So 2 millimeters is much, much greater than 2 microns. It's 3 orders of magnitude larger. Do y'all follow me on this? Now, because of that, all the actual current that's flowing will be contained in 1 skin depth of the surface. I did this last time, right? Y'all remember this, everyone? So the only thing we have to change from the DC formula, the length is per length, so nothing there. Sigma is sigma. It's just the area. Do y'all follow me? And do you remember how I said to do this? If you just cut this thing and rolled it out, the length here would be the circumference, or it would be 2 pi times A, and the thickness here would be a skin depth, and that would be the area. Do y'all remember that? So it's a skin depth times 2 pi A. Therefore, the AC resistance here would be 1/sigma, 5.8 times 10 to the 7th, times 2 pi times the circumference, which would be, 2 pi times A, which is 2 millimeters. And then it's times the skin depth, which is 2.09 times 10 to the minus 6. And that would be the AC resistance. Can you give that to me? 0.66, did you say? And you can see it's significantly higher than this. This is 660 milliohms per meter. This is 1.372 milliohms. And the reason is the area is now much less that the current flows in. And then the limit, you can see here, as frequency tends to infinity, the resistance goes to zero. Or, I'm sorry, goes to infinity. The resistance, the area goes to zero, the resistance goes to infinity. Y'all follow me on that, class? Just to be aware of that thing. Now, the first time I really saw, you might say, how this affected designs, I was a grad student and I was doing work on a plasma etching system. And it was at 13.56 megahertz, which is a low frequency. But even at that frequency, the piping used to connect the power to the actual reactor was hollow. It was hollow. But they could use that to run a coolant through it. Because remember, if nothing flows in the center of something, you don't need to put copper there or any kind of metal, right? You just put it where you need it, and they had hollow piping, and I remember that very well. So it's something that you may encounter if you have anything that is going to be high power. And I believe for most of the microwave systems that I'm aware of, all the piping and things like this where they're actually they're connecting power amplifiers and things like this, they will be hollow if the power is significant in any way. And I'm trying to think of a good example of something I've dealt with. I've never opened up a microwave oven and taken a look. I know there's a waveguide that feeds the oven usually, and that is, in a sense, taking care of that problem. But anyway, that's that problem. Is there another part to it? All right. Now, I also put some of my own on there, right? And y'all follow that, what I did? Okay, good. Any other questions?
Did you do the second one, the one that you put on there?
You're gonna, yeah, let me erase this. I created those on my own.
The coaxial transmission line is made of copper and driven at 10 megahertz. Inner radius of 1 millimeter. And an outer radius of 4 millimeters. Determine the resistance per meter. That's perfect.
And this is assuming some thickness out here too. So this is copper and this is copper. And the only thing we need is the resistance per meter, right? I think that's right. Resistance per meter. So the idea is this. This is a transmission line, so current could be going down the central core and returning in the outer sheet. Y'all follow me on that? So you need to calculate the resistance per meter of the inner core and add that to the resistance per meter of the outer core. Y'all follow the idea? All right. For the inner core, the resistance per meter is going to be the same as what we just did in terms of the actual matter-of-fact calculation. So when we take a look at our resistance of the core, this is the AC resistance. It's going to be 1 over sigma, and then it's going to be times 2 pi times the radius, which would be A, times the skin depth. So now we have to go back and get the skin depth again. What's the frequency?
10 megahertz.
So that means the skin, and this is copper, the square root of pi f mu sigma. And can you just tell me what that is? Mu is 4 pi times 10 to the minus 7th, and sigma is 5 point. Sigma is equal to 5.8 times 10 to the 7th. Siemens per meter. I want to say one thing. You're going to see slight changes in that because many times you don't get just pure copper. It may have a bit of alloying in it. So you'll have, maybe it'll be 5.6, 5.5. And there's other temperature effects. There's a lot of different things. But basically, if you look in the back of Wentworth's book, when he lists the conductivity for copper, he doesn't make any qualifications. He just has this 5.8 times 10 to the 7th. 1 over ohm meter or Siemens per meter, and that's pretty much standard because that's pure copper. And they do alloying and stuff. Now, if it was steel, if it was 1045 steel, which is very common for a lot of things, the conductivity would be 5.8 times 10 to the 6th. It would be an order of magnitude less for 1045 steel. But also with steel, what happens is the permeability would be, the relative permeability would be 1,000. So that would have a strong impact on this value right here. You all follow me? Order of magnitude less here, but 3 orders of magnitude greater here. So the overall effect would mean the skin depth would be even less in 1045 steel. Just keep that, or 1040 steel, pardon me. You know, the real big deal with steel is it's strong. Tensile strength is phenomenal. Pure copper you can pull apart with your hand pretty easy. You can't do that with steel wire. So oftentimes, if they have any kind of wire that's hanging, or something that's got to support a lot of weight, they'll have a stainless steel core and a copper cladding on it if they want to conduct electricity through it. Just remember that. Now, I'm not even sure what the power lines that are used by the power companies, how they're built, but they usually have steel of some sort. It could be woven steel, but a steel in there basically for its tensile strength. And they will use it to conduct, but you know, steel is just not that good of a conductor. Okay, so what do we get for the skin depth?
20.89 micrometers.
2.89?
20.89.
Oh, sorry.
Micrometers.
20.89 times 10 to the minus 6 meters, okay? For this one, A was 1 millimeter. So you can give me this value, right? That's for the core. I don't know. I've got the calculation done. You can look if you've got access to it. Just tell me. Or you can calculate, make sure it's right.
I'm not sure if the core is that.
Pardon me?
Overall, I think you'd given the overall.
All right, well, let's just get for the core first. This is just the inner conductor. Anybody? No? One over 2 pi A times skin depth times sigma. 0.949, and that would be 1 over, or would that be ohms per meter? Now, what about R? And this would be of the, you might say the outer cladding. It's going to be the same exact form. It's 1 over sigma, but now it's not 2 pi A, it's what? 2 pi?
I think it's actually 0.131 for that value.
0.131?
Yeah.
Okay. And then for this outer, you get the return resistance. Remember, current's flowing this way and then back this way. Now we have to go one skin depth deep here, and that means the only thing that changes, it's still gonna be 1 over sigma, then it's 2 pi, and then it's gonna be times b times the skin depth. So the only thing that's changing here is this dimension, it goes to b. Y'all follow me on that? It's probably 1/4 of that. I think it has to be.
1033.
Therefore, the total is R total is what? 0.163. Is that right? 164, pardon. Is that right? Is that what the answer is? Okay. Really, those problems, once you do a few, all of them fall suit. There's nothing tricky about it. The only thing, here's the trick. Not trick, really, you just have to be attentive. This could be made of copper, this could be made of steel. Follow me? It could be different materials. Has to be the same frequency. Mu could change too. If it was steel, if it was 1045 steel and the mu changed, then you'd have to change mu in there too. All right? If mu relative was 1,000, say. Okay? That's it. Any questions? All right, now, today what I'm going to do is talk about power flow, power density really, but I'm going to contrast a bunch of stuff. This is something, it's not the way Dr. Wentworth's book does it, but I think it's very helpful to see it this way. And please take good notes. This is an important lecture. So I'm going to stick with his standard way of denoting things. And he says, you know, if you have an electromagnetic field polarized in the x direction and it's propagating in the z direction, the E field would be given as simply some E naught e to the minus alpha z times e to the minus j beta z, and then it's going to be ax. That's the phasor form of the E field. Y'all follow me on that, class? It's propagating in the z, but it's oriented in the x direction, right? Now that's a standard plane wave, and it comes from a solution to Maxwell's equation with the assumption is that we're far from the source and we have an E field of only one, with one polarization really, with one component that's propagating in the z direction. Now, this E field itself is associated with a power flow. There's also an H field, right? There's an H field here. Please write this down. The H field would be equal to some E naught, and it would be divided by eta. And remember, eta can be complex. Then it would be times e to the minus alpha z, and it would be e to the minus j beta z. And we know that E crossed H has got to be a vector in the direction of propagation, which would be z. That means the H field itself would be in the AY direction. The E field has the units of volts per meter. The H field has the units of amps per meter. And this is the standard form. Y'all follow me on this, class? We've gone through this many times, right? Okay, now I'm going to add a little something to this. Because eta, in general, eta is equal to the square root of j omega mu over sigma plus j omega epsilon. Eta has some magnitude, and it is at some angle. Now, I'm showing you, this would be the general form, right? But we know it can be complex, so it would have a magnitude of eta, and it would also be at some angle, because it's complex. Y'all follow me? Possibly complex. Y'all agree with that? All right. Now we get into power flow. When we talk about power flow, we really talk about power density. Density of a wave. And when you think about power density, it's power, but it's not just power in watts, it's power per meter squared. So the formula, and this is in the phasor domain, the average power of this, of an electromagnetic wave that's propagating would be equal to 1/2, and then it's the real part of E, the E field in the phasor domain, crossed into the H field, but the H field is conjugated. Y'all follow me on this, class? Now, this is very similar to something you're used to seeing in power. Remember, if you had gross power was equal to what? 1/2 the real part. This is going to be average power. Real part of V times I conjugated. Remember that? V times I conjugated had a real power and had a reactive power. Right? The real part of it is the actual power that's flowing. Reactive power doesn't flow. It's energy that comes in and out. So this is the real power that's flowing, the average power. The units are watts per meter squared. I'm going to keep expanding this. So PAV, now watch this is important, is 1/2 the real part of the E field. There's the E field. I'm just rewriting this. But now I need the conjugate of this. What is the conjugate of that? Because it's got to be crossed into it, by the way. It says cross right here. But what would conjugation do to this? Let me do it this way. I'm going to go ahead and let me write the H field as such. Magnitude of eta, and that would be e to the minus alpha z, e to the minus j beta z. And then it would be e to the minus j, and it would be the angle associated with eta right here, in the AY direction. The only thing I've done here is I put the magnitude of eta, and then I took, normally it'd be magnitude of eta times e to the j and the angle associated with this. And I took it upstairs, so it's the minus there. Do y'all see this, class? How many understand what I've done there? Y'all with me? That far back? All right. Now, what would the conjugate of this be? Take a look at, what does conjugation do? If I had, say, A was 20e to the j pi over 4, what is A conjugate? Anyone? Magnitude's still 20, right?
Negate your angle.
Minus j pi over 4. So anything with an imaginary, any component that's imaginary flips the sign when you get conjugation, doesn't it? Y'all remember that? So when I take the conjugate of this, the E naught magnitude stays the same. So I'm going to have E naught. The magnitude of eta stays the same. This e to the minus alpha z is strict real. It stays the same. Now with conjugation, this e to the minus j beta z becomes e to the plus j beta z. And this term, e to the minus j at that angle, becomes e to the plus j. Angle associated with the complex impedance, intrinsic impedance. Just write that down. This all kind of shapes down a very easy formula to remember, but this is how you get it. So I've got the E field and I crossed it into the conjugate of the H field. Can you all see this all right? Do you need me to write larger? I mean, if you do, I will. I'll try it.
Why did the alpha z stay negative?
Pardon?
Why did the e to the alpha z? Oh, because there's no j there. Never mind. I got it.
It's strict real, so you don't
Yeah.
change. Remember, alpha is real. anything with a J in it changes, basically. All right, now, look here for a second. What happens when you take a look at this, and you take a look at e to the minus j beta z times e to the plus j beta z? They go away, don't they? That's e to the 0, which is 1. Do y'all follow me? Everybody follow me? So the e to the minus j beta z, e to the plus j beta z are eliminated, thankfully. Now, next thing you notice is I have ax, yeah, I should have had an ay here. I don't know if I did, if I erased that. I have ax crossed into ay, that is az. The direction of power flow is the direction of propagation always. So I'm going to take this and put it out here. I know the answer is going to be in the az direction, that's the component. Now I have 1/2 that stays there. Now look here. The real part, well, E naught is here and E naught is here, is it not? That's a scalar magnitude. So it's E naught squared. Eta is also scalar. So it's going to be 1/2 magnitude of eta naught, or E naught squared, over magnitude of eta. And then I'd also have e to the minus 2 alpha z. And you can see why. There's an e to the minus alpha z and e to the minus alpha z. It'd be e to the minus 2 alpha z. Do y'all follow? So I take that out here. And then I'm left with just the real part. Here's where I got to figure out. What is the real part of e to the j theta n? What's that going to be? Just cosine. Y'all follow me? You can take e to the j theta and break it into cosine theta plus j sine theta. The real part is just the cosine of that. Y'all follow me? Just the cosine. So now it's going to be cosine of the angle associated with eta. And this would be in the az direction, and it would be watts per meter squared. So it's power per area. That's flowing. So if you have an electromagnetic wave, if I've got an antenna, I'm propagating it at you, that means that the power density coming at you would be this in watts per meter squared. Usually, in anything that's realistic. Atmosphere, free space, vacuum. Alpha is 0. And this is strict real, so the cosine of that is just 1, and it's simply, I'm just going to tell you this, if you're talking about propagation in free space, and I'll put it here, or in a lossless medium, then this itself, the average power density, simply is going to be 1/2, and then it's going to be times magnitude of E squared divided by eta if it's losses. And it will always be, I just put AP here, it's the direction of propagation. The energy propagates and the wave propagates. So that would be in watts per meter squared. Now something that's just power density. If you take a look at this, that's lossless medium. If you have something that's a good conductor, I'm going to do that over here. So if I have a good conductor, that means sigma is much, much greater than the mega epsilon, right? We're going to talk about this right here. Power flow in a good conductor. And the first thing you have to do is get eta. And that's the square root of j omega mu over sigma plus j omega epsilon, right? Now, if it's a good conductor, how do I reduce the complexity? Anyway. Yeah, the j omega epsilon go away, right? Y'all follow me? Now I have this. Well, I've got square root j Well, square root of j is really what? It's e to the j pi over 4, or 45 degrees, isn't it, class? So I can say this right here is really equal to the square root of omega mu over sigma, and then I have e to the j pi over 4. That means the angle associated with eta is simply pi over 4. Y'all follow me? I got a magnitude and an angle, correct? Times e to the j angle. Correct, class? All right. Now, if we've got that, the next thing we need is gamma, or the propagation constant, which is alpha plus j beta. Remember, that's equal to the square root of j omega mu times sigma plus j omega epsilon. And if it's a good conductor, what do I do again? People? That's right. This goes away. And I have just sigma here, right? And that means that alpha, this is what it comes down to, alpha is going to be equal to beta, and it will be equal to the square root of pi f mu sigma. Now, I didn't do all the steps there, but I've done it before. Do y'all follow me? If you break this up, j is equal to 1 plus j over the square root of 2, right? Take the square root of 2 inside. You get 2, you get omega is 2 pi f over 2 is just pi f mu sigma. Can you all see this? Okay. Now again, now I've got alpha and beta, right? Now I come over and I'm going to get the power flow in a good conductor, and I'll do it right here. So it's 1/2 magnitude of eta. Well, here's eta. The magnitude of eta is just square root of omega mu over sigma. Then it's going to be, and I'm using this one, times E naught squared, whatever E is, times e to the minus 2 alpha z. Well, that's alpha. I'm just going to leave it as alpha though, because it's given as this. Then it's going to be times cosine of the angle. Now take a look at this. The angle is 45 degrees, right? Pi over 4. What's the cosine of 45 degrees? 1 over square root of 2, correct, class? So then I take this and I multiply it by 1 over the square root of 2. And the direction is AZ. And the units are watts per meter squared. This is the thing to take from that. Now, I don't just have a half, I have a half, and then also I've got a 1 over square root of 2 factor in there. And the magnitude of eta itself may be much, much less than 120 pi. As a matter of fact, it can be below 1. It can be less than 1, right? Which just gives you an idea of how, if you get a good conductor, how different it is for power propagation. By the way, the velocity goes way down too, right? Phase velocity in a good conductor. A lot of things change when you talk about power flow in a good conductor or in a very lossy environment. That's what I want to talk about in terms of power flow, contrasting it from a good conductor to really just a lossless medium and the general equation. Now, that's just power. Now we're going to talk about 3 other things. We're going to talk about the energy density in the electric field, the energy density in the magnetic field. Density means it's not flowing, it's there, right? I mean, energy density. And then also the power dissipation that's occurring in any kind of velocity material. So first, I'm putting these all here because it's the perfect place to do this all at once. So we've done power flow, and that I'm going to redo it up here. PF is equal to 1/2 E naught, you don't have to write this down if you don't want to. That's powerful. Watts per meter squared. When we talk about power, and I'll put this down, power field. It's really power density. When we talk about power dissipation, all right, think about what is the power dissipation in a resistor if you have a current I. Say it's DC, what is it? I squared R, that would be in watts, right? All right, when we talk about power dissipation, you can call it P dissipated, that would be watts per meter cubed. This is dissipated now, it's not flowing, it's being dissipated in the environment, turned to heat. That's equal to J dot E. And by the way, I should have said, if there was a voltage here, V, then the power here would be V times I, right? And technically, I mean, this is for DC, I should conjugate it if it's AC, but y'all follow me how that would be the case? Because J is amps per meter, E is volts per meter, so I have amp volts per meter squared, and that's watts per meter, or yeah, watts per meter cubed. I come down here, and now I'll replace J with sigma, and that makes it sigma times E squared, magnitude of the E field squared. Can you all see that okay? I'm just replacing J with sigma E. You all follow? You write it a little larger. Power dissipation is equal to sigma times magnitude of the E field squared. And that's in watts per meter cubed. That's dissipated. It's turning to heat. After you got power dissipation, now I want to talk about when you have any electrostatic field or propagating field, it doesn't matter, there's going to be an energy density. If you took a snapshot in time and just looked at the E field, you'd find what the energy density is. The electric energy density is, they use omega sub E usually, just for electric field, and it's 1/2 epsilon times the magnitude of the E field squared. And that would be in joules per meter cubed. Then when you talk about the magnetic fields, that's 1/2 times mu times the magnitude of H squared. And it would be in joules per meter squared, per meter cubed, pardon. Are you all with me? Those are scalar quantities. So if you know the electric field, if you want the energy density at that point, it's 1/2 epsilon E squared. If you've got the magnetic field and you want the energy density, it's 1/2 mu H squared. We use this and this to calculate capacitance and inductance before, but I'm redoing this. So now you take a look at the equations. Power density, right here. It's flow, right? Then there's power dissipation. If it's a lossy environment, you have an E field, you have current conducted, a current density, you're going to have power loss. Here's the energy density and both the electric and magnetic energy density. And something interesting happens right here. And I'm going to show you this right here, because this is kind of interesting. So we've been talking about propagating waves. These energy densities are true if they're non-propagating. Remember I talked about a capacitor. You just charge it up. There's an electrostatic field about it, right? All that electrostatic energy you can get back, correct? If you went ahead and found the electrostatic energy density at every point around that capacitor and between the plates and integrated it, it would be a total energy that you have available to dump back into a resistor and dissipate. And same with an inductor with the magnetic field. But if you have a propagating wave, this is the interesting part. Remember, concepts like electric field, magnetic field, they're abstract. I mean, we can't visualize that, we can't look down and see it. We have sensors that can detect this and that they tell us what they are. But we know that the E and H field are, for a propagating wave, are linked. They are properties, the properties that they have are given by the photons that carry that. And photons, they don't have magnetic photons and electric photons. They only have one type of photons, and it renders as either a virtual or a real photon. And I'm not gonna go there. But when you have an electric field propagating, if you just have an electric field in this direction, and it's propagating this way, I know the electric field can be given, matter of fact, I don't even need to say anything more. I know if I'm in a region, I'll have an H field that'll be equal to the E field over eta. And I'm not even gonna bother with the vector signs here. I'm just gonna say that would be the magnitudes. Y'all follow? Now, how much energy is in that? Energy density, just at this point in space-time. Well, the electric energy density would be 1/2 epsilon times the E field squared, right? That would be in joules per meter cubed. Follow me? What's the magnetic energy density from that wave? Well, it would be 1/2 mu, and then it would be the H field. Well, the H right here is just going to be E over eta squared, right? Y'all follow me? You'll see what I'm doing. I'm gonna work with this one. So that means I got 1/2 mu E squared divided by eta squared. Follow me? Now I'm going to substitute in, we're going to assume this is lossless for now. Or else it gets there's a little too much to this. But if it's lossless, then I can say this is equal to 1/2 mu divided by eta. Well, eta then is what? Square root of mu over epsilon. If I square that, I get mu over epsilon times magnitude of E squared. Hope you're following me on this, right? Here, the only thing I've done is replaced eta squared with mu over epsilon. Follow me, guys? What do you notice happening here? I get 1/2 epsilon times magnitude of E squared. The energy in the electric field is the same as the magnetic field. All right, so they each carry this, it's the same electric energy density is the same as the magnetic field's energy density at a point space-time. That's true always for photonic, any kind of power flow. Whenever you have propagation, stuff like this, there isn't more energy in the magnetic field and less energy in the electric field, all right? They're the same when it's propagating. Just, this is a point of interest. Later, you may understand some of the implications of this. Now, that's not true when you have a capacity. When you have a capacity, you technically don't have to have any magnetic field. You can have just charge hanging out that creates a static electric field. No magnetic field whatsoever. All the energy is in the electric field. If you have a wire with a current that's not time varying, or an inductor with a current that's not time varying, then all the energy is in the magnetic field. But here, when it's propagating, equal amounts of energy in both. So that's sort of a takeaway from this. Now, I covered, I didn't think I did, but I did. I'll give you some homework on this. And I'm going to tell you I'm going to stop there for now. I'll give you homework, and the one thing I'll tell you about, if you're going to have to know skin depth, resistance, and understand how, when I give you homework, how to solve the problems related to this stuff I just covered, okay? For Friday? Good deal. Anybody got any other questions? Because we are, really material-wise, I'm going to do a few more things, but we're pretty much done with all the material we're going to cover this semester. We've gone through, and I'll do one or two other things, but I'm not going to do general propagate or reflections and things like this. That is supposed to be for EMAG 2, but I didn't want to go through the end of chapter 5, just have you turn the crank on all these crazy equations. Because it doesn't help the understanding. Any other questions? Any idea why so many people are missing?
No idea.
Nothing, huh? It's a nice day. Maybe that's it, they're off the hull of the lake. I see myself. Anyway. All right, guys.